From counting apples to calculating the speed of light, numbers come in all shapes and sizes. And today, we're going to take a journey through the top 10 most important number sets that you need to know, starting with the smallest and working our way out to the biggest of them all. Must-know set number 1, the natural numbers. The definition of natural numbers is that they are the counting numbers starting at 1. And in set notation, we use the capital letter N to represent the natural numbers. And then inside curly brackets, I can start listing the numbers in this set. Remember, the natural numbers are the counting numbers that start at 1. So the numbers in this set would be 1, 2, 3, 4, 5, and so on. Now let me place some natural numbers on this number line I have drawn below. And on the left, inside this circle, I'm going to list some examples of natural numbers. And these natural numbers are very important because they're used for basic counting, like counting objects or steps. And natural numbers are actually going to be a subset of a lot of different sets of numbers we're going to look at throughout the rest of this video. And as we look at more sets of numbers, this Venn diagram on the left is going to get bigger, and we'll be able to fill in more numbers on this number line that I have at the bottom of the page. So let's move on to our next set. Must-know set number 2 is the whole numbers. The definition of whole numbers is that they are the natural numbers plus 0. And in set notation, we use the capital letter W for whole numbers, and the first whole numbers would be 0, and then the natural numbers 1, 2, 3, and so on. So on my number line, the set of whole numbers would include all of these natural numbers, but also the number 0. So let me add the number 0 to the number line. And now these values are all whole numbers. So notice within the set of whole numbers are natural numbers. So natural numbers are a subset of the whole numbers. And that's also clear in the Venn diagram we have here. Notice the natural numbers, the counting numbers starting at 1, are within the set of whole numbers. The only number that is a whole number that is not within the natural numbers is the number 0. So let me add that within the set of whole numbers, but outside the set of natural numbers. And the notation for indicating that the natural numbers are a subset of whole numbers looks like this, where in this statement it says that the natural numbers are a subset of the whole numbers. This sideways U means a subset of, and that just means all of the natural numbers are within the set of whole numbers. Right, even just looking at this set of whole numbers here that I started, all of the natural numbers would be in this section. They're all within the set of whole numbers. Now, the importance of whole numbers is that they include 0, which is essential for representing the absence of quantity and for serving as the additive identity in arithmetic operations. And whole numbers actually fit inside an even bigger set that's coming up next. Must-know set number 3, the set of integers. The definition for this set is that it is the set of numbers consisting of 0, the positive counting numbers, and the negatives of the counting numbers. In set notation, the capital letter Z is used for integers, and the numbers in this set would include the negative counting numbers like -3, -2, -1, also include 0, and the positive counting numbers. So notice within this set, we have all of the whole numbers and all of the natural numbers. And that's indicated by this Venn diagram on the left. Within the set of integers is the set of whole numbers, and within the set of whole numbers is the set of natural numbers. So we could summarize that by saying the natural numbers are a subset of whole numbers, which means all of the natural numbers are within the set of whole numbers, but also the set of whole numbers is a subset of the set of integers. All of the whole numbers are within the set of integers. So I can say the whole numbers are then a subset of the set of integers. And then let me add the negative integers to the number line below. So all of these values on the number line are integers. And let me also add some values to this Venn diagram. Inside the set of integers, but outside the set of whole numbers, would be the negative integers. So for example, -3, -2, -1. Those are all integers, but they are not whole numbers. And now integers are very useful for situations involving both positive and negative quantities. such as temperature changes or financial gains and losses. If we keep moving on, we will see that integers are actually a subset of an even larger set of numbers. Must-know set number 4, the set of rational numbers. The definition for this set is that it is the set of all numbers that can be written of the form p over q, where p and q are both integers and q is not equal to 0. Now, there are lots of different types of numbers that can be written in this form, p over q, where p and q are integers. Right? This basically just means any number that can be written as a fraction. Now, any integer can be written as a fraction, just as a fraction where the denominator is equal to 1. But there are lots of numbers that can be written as a fraction that are not integers. So the values that would lie outside the set of integers but within the set of rational numbers would be values like 1 over 2, which on a number line would be down here between 0 and 1, or negative 7 over 4, which as a decimal is negative 1.75, so that would fall about right here on the number line. And actually, any decimal value that terminates or repeats could be written as a fraction. So for example, the number 7.3 repeated, where that 3 just keeps repeating forever, could be written as a fraction. 7 and 1/3 as a fraction is 22 over 3. And on a number line, that 7.3 repeated would fall about right here. And let me make a note that rational numbers include decimals that terminate or are repeating, because those decimal values could be written as a fraction of that form p over q. And looking at this Venn diagram, we can see that the set of rational numbers includes all of the integers, which includes all of the whole numbers, which includes all of the natural numbers. So we can summarize that by saying the natural numbers are a subset of whole numbers, which are a subset of the integers, which are a subset of the rational numbers, which we use the letter q to represent rational numbers. So all of the integers, whole numbers, and natural numbers are within the set of rational numbers, but so are values like a half, negative 7 over 4, and 7.3 repeated. Those are also rational numbers, even though they're not inside the set of integers. And rational numbers are very important because they're used when precise ratios or measurements are needed, such as in recipes or in construction. And these rational numbers are actually a subset of an even bigger set called real numbers. But before we talk about real numbers, let's talk about another set called irrational numbers. Must-know set number 5, the set of irrational numbers. The definition of irrational numbers is that they are numbers that cannot be written as a ratio of two integers. So basically, they can't be expressed as a fraction. And there are some really famous irrational numbers. For example, pi, or Euler's number e, or let's say the square root of 2. Those are all examples of irrational numbers. They can't be expressed as fractions where the numerator and denominator are both integers. And in fact, their decimal values would go on forever without repeating. And if I were to place these values approximately on my number line, well, pi is about 3.14, the value of e is about 2.72, and the value of root 2 is about 1.41. Now, it's important to note that all of those values were just plotted approximately on this number line. Their actual decimal values would go on forever with no repeating. So there's no way to express any of those values as a ratio of two integers. They can't be expressed as a fraction. And when looking at the Venn diagram, notice that these irrational numbers don't overlap at all with the set of rational numbers. So that means there are no numbers that would fall within the set of rational numbers and the set of irrational numbers. A number can't be both rational and irrational. It's one or the other. So the intersection of q and p, which we write like this, q and then an upside down u and then p, that means the intersection of those two sets, is equal to the null set. There are no elements in the intersection of those two sets. And these irrational numbers are actually very important numbers that often appear a lot in geometry, physics, and engineering, like when calculating the circumference of a circle. Must-know set number 6, the set of real numbers. The definition for this set is that it is the union of the rational and irrational numbers. So if we were to make a set that combines all of the rational numbers and all of the irrational numbers, we would have the set of numbers called the real numbers. And in set notation, we can write the union of those two sets. Well, rational numbers, we use the letter Q, and then for union, we use a U, and then irrational numbers, we use P. So this means the union of both the rational and irrational numbers. So every real number is either rational or irrational. It has to be one or the other, but it cannot be both. So I could indicate those are both subsets of real numbers. The rational numbers, Q, are a subset of the real numbers, and the irrational numbers are also a subset of the real numbers. And if this number line continued forever to the right and to the left, every real number possible would have a spot on that number line. And the importance of real numbers is that they are used for any kind of continuous measurement, such as distances, weights, and time. And now let's move on to our next set, which is actually separate from the set of real numbers. Must-know set number 7, the set of imaginary numbers. The definition for this set is that it is the set of numbers that are real multiples of I, where I represents the square root of -1. Now, if you were trying to evaluate the square root of -1, you'd be looking for what number, when you square it, do you get a result of -1? Well, there's no real number that when you square it, you get a result of -1. So therefore, we define the square root of -1 as an imaginary number, and we use the letter I to represent that imaginary number. And that imaginary number I, if we square that, we would get -1. So some examples of imaginary numbers would be any real number multiplied by I. So for example, inside this set of imaginary numbers, I'll list some real multiples of I. For example, 3i, 2i, or -4i. And notice this set of imaginary numbers has no overlap with the set of real numbers. There are no numbers that are both a real number and an imaginary number. So we could say the intersection of those two sets, the real numbers and the imaginary numbers, is the null set. And notice that capital letter I represents the set of imaginary numbers. And since imaginary numbers can't be shown on a regular number line, we have to add a vertical axis to be able to plot imaginary numbers. So the horizontal axis is for the real component of a number, and the vertical axis is for the imaginary component. So if I were to plot a point at 3i, it'd be right here at 3 units on the imaginary axis. And why do we care about these imaginary numbers? Well, they're used often in electrical engineering, quantum physics, and signal processing. And even though these two sets, the sets of imaginary numbers and real numbers, are disjoint, they are both subsets of our next number set. Must-know set number 8, the biggest set we're going to work with, the set of complex numbers. The definition for this set is that it is the set of numbers of the form a plus b times I, where a and b are real numbers. So for example, the number 3 plus 2 times I is a complex number. It's a real number plus a real multiple of an imaginary number. So it's of this format, a plus b times I. But often complex numbers would fall into either the subset of imaginary values or real values. It would be an imaginary value if it didn't have a real component. So if the a value in a plus bi was 0, then it would just be an imaginary number. But if the imaginary component was gone, so if b was 0, the b times I component would be gone, and you'd be left just with the real value, a. So if b was 0, it would fall into this subset of real numbers. But if a and b are both non-zero, like this example I made up here, 3 plus 2i, it falls within the set of complex numbers, but outside the subsets of imaginary and real numbers. So an important thing to note is that both imaginary numbers and real numbers are subsets of complex numbers, but there are some complex numbers that are not either real or imaginary. And to represent a complex number, we need a real and an imaginary axis. So if I wanted to show where 3 plus 2i would be, its real component is 3, so I would move 3 along the real axis, and then its imaginary component is 2. So I would have to move 2 along the imaginary axis, and that would bring me to this point right here. Now, complex numbers are very important because that set of numbers makes up every other subset that we've talked about. Real numbers, whole numbers, natural, integers, rational, irrational, imaginary, those are all subsets of complex numbers. Must-know number set number 9, the set of prime numbers. Remember back to the beginning of the video, the first set we looked at was the set of natural numbers. The set of natural numbers were the counting numbers starting at 1. So like 1, 2, 3, 4, and so on. What we're going to do in this section is look at a subset of these natural numbers. We want to look at the set of prime numbers. If you don't know what a prime number is, the definition is that they are a special subset of natural numbers greater than 1 that have only 2 factors, 1 and itself. So in set notation, the set of prime numbers would be looking for numbers that are bigger than 1 but only have 2 factors, 1 and itself. So for example, the number 2, its only factors are itself 2 and 1. 3, the only factors of 3 are 3 and 1. 4 is not prime because the factors of 4 are itself 4, 1, but also 2 divides evenly into 4. So 4 is not prime. But 5 would be prime. Its only factors are 5 and 1, and 7, 11, and so on. And if I remind you of the set of natural numbers, notice every prime number can be found in the set of natural numbers. 2, 3, 5, 7, 11. Every prime number will be found in that set of natural numbers. So the set of prime numbers are a subset of natural numbers. So in the Venn diagram here, I'll draw a subset within the set of natural numbers. And I'll list some prime numbers within that subset. And then outside the set of prime numbers, but within the set of natural numbers, I could list some numbers that are natural but not prime. So for example, 1, 4, 6, and so on. Now, prime numbers are really important when it comes to cryptography, computer science, and number theory. Must know number 10, the Venn diagram of how all these number sets fit together. Remember, the outermost set was the set of complex numbers. The set of complex numbers, we use the letter C to represent the complex numbers, and they're the superset of all the other sets we looked at. Complex numbers are of the form A plus B times I. So a complex number could look like this, 3 plus 2 times I, where the A value, which in this case is 3, is the real component of the complex value, and B times I is the imaginary component of the complex number. Now, if the complex number has an A value of 0, that would mean it doesn't have a real component, it would just have an imaginary component. And that brings us to the set of imaginary numbers. And an imaginary number looks like this, like 3 times I or 5 times I, a real number multiplied by I, where I, remember, is the square root of -1. Now the next set of numbers that we looked at was also within the set of complex numbers, but it was disjoint from the set of imaginary numbers. It was the set of real numbers. The capital letter R is used for the set of real numbers, and they don't have an imaginary component. So within the complex number set, if the value of B is 0, that would mean there is no imaginary component to the number, and it's just a real number. And all real numbers fall into one of 2 subsets. It's either an irrational value, where the letter P is used to represent irrational values, and those are just numbers that cannot be expressed as a fraction of 2 integers. So for example, pi or root 2. And if a real number is not irrational, then it has to be rational. And for rational numbers, we use the letter Q. Rational just means it can be expressed as a fraction of 2 integers. So for example, a half or 3/4, or any decimal value that terminates or repeats. So 1.3 repeated could be expressed as a fraction of 2 integers, so it's a rational number. Now further within the set of rational numbers, we have the set of integers. The letter Z is used for integers. Integers include 0, the counting numbers, and the negatives of the counting numbers. So for example, -3, -2, 0, 5, those are all integers. But I didn't write 0 or 5 in that subset because they fall into a further subset that we looked at, the set of whole numbers. The set of whole numbers include 0 and all of the positive counting numbers. But those positive counting numbers also fall within this subset, the set of natural numbers. So for example, 1, 2, 3, those are all natural numbers. Those are the counting numbers. Oh, and I forgot, for whole numbers, we use W, and for natural numbers, we use N. And that's the end of our journey through all of the most important number sets. Thanks for watching. Make sure to subscribe for more math videos.